Hello, and welcome to this lesson on multiplexers. So let's just jump right into it. So suppose I have two input signals. Let's call them I0 and I1. And I only have one output signal. Let's just call it Y. Now what I want to do is be able to pick between I0 or I1 for what I want to feed to Y. So effectively what I want to do is build a switch that connects all of these guys together. So it might say that the switch is sort of normally connected to I0, but through application of a signal, we can cause it to switch to I1. And let's go ahead and give that switch just the letter S, select. So we're going to say that Y is equal to I0 if S is equal to 0, and I1 if S is equal to 1. So this is what we want to make. So like we've done this whole time, let's go ahead and throw it into a truth table and see what we get. Although I think this one makes enough intuitive sense that you can probably guess what the output is going to be, but let's go ahead and do it anyway. Let's have S, I0, and I1 on the input side. And then to populate the Y side, remember, when S is equal to 0, we want Y to be equal to I0, so that'll be 0, 0, 1, 1. And when S is equal to 1, we want Y to be equal to I1, so that would be 0, 1, 0, 1. So we can write that as our generalized expression of midterms. So we'll say that Y is equal to a function of S, I0, and I1, and is equal to the sum of midterms, 2, 3, 5, and 7. So we'll go ahead and throw that into a K-map. So let's go ahead and build our K-map here. And we drop our midterm values into the cells. So that will be 2, 3, 5, and 7. And let's go ahead and set up our solution here. Y is a function of S, I0, I1, and is equal to, let's go ahead and grab these guys first, 2 and 3. So we see that we can make two boxes of 2. So that'll be equal to S naught and I0. Then we'll have or something. Then let's group 5 and 7, and that will give us S and I1, which is probably what we expected, right? When S is equal to 0, we get I0, and when S is equal to 1, we get I1. So let's go ahead and build that circuit out to see what it looks like. We've got our, let's start with our S signal. Comes in. Now we've got S naught in this circuit, so we'll need to break it out and get our S naught. So I'll sort of take that off. There's our S naught. Now we've got our two AND gates for I0 and I1. It's ANDed with I0 and I1. And then finally, we have our OR gate to wrap everything up, and that's our output Y. So there's our basic structure for this multiplexer. Now you might notice some familiar constructs there. For example, right here, a 1 to 2 decoder like we talked about in the last lesson. And this block here, we haven't really talked about before, but it has a name. It's called an 2-bit enable. And then of course, we kind of end with an OR gate like we do in a lot of combinational logic circuits. So what's helpful about multiplexers is that we can reuse the structure over and over again, right? We don't have to go through the whole process of getting our truth table and our midterm expression and our K-map, right? We can just build this structure off by having a sort of generalized template. So let's go to see what that template looks like. So this particular circuit that we just built is called a 2-to-1 multiplexer. So if we were to have, let's say, an n-to-1 multiplexer, where n could be some number, it might look something like this. Well, we'd start with a k to n decoder, right? which is going to take a select and S signal that is k bits large, and it will produce an n-bit decoded signal. And we'll feed that n-bit decoded signal into an n-bit enable, along with n bits of input that we wanted to select. And the output produced here is also n bits, right? Every input enabled with every select input from the decoder, and all of that feeds into an OR gate to get us our output Y. So there's our basic sort of generalized template for an n-to-1 multiplexer. By the way, we don't need to draw this every time. There's a schematic symbol for the multiplexer, and it's basically just a trapezoid. So you'll have that n-bit input coming out, that single bit of output Y, and then our k bits of select going in. So that's our basic schematic symbol for a multiplexer. Now last, before we let things go, let's kind of do an example just so we can see how we use this template. Let's go ahead and build a 4-to-1 multiplexer, or MUX for short. So let's start at the top. That means we're going to need to have, if n is equal to 4, then we're going to need a 2-to-4 decoder, which will take 2 bits of input, S0 and S1, and it will produce 4 bits of output. Remember, those correspond to S0 naught, S1 naught, S0 naught, S1, S0, S1 naught, S0, S1. Now we'll need our 4 bits of enable, so that's just 4 AND gates, I0, I1, I2, and I3, and each of the individual inputs from the decoder, outputs from the decoder. And then we finish it off with our 4 input OR gate and our output Y. And there we have it. There's our 4-to-1 multiplexer. Like I said, it's got a simple structure that's easily sort of templated and generalized. So anytime you need to make a multiplexer of any size, if you had a 64-bit multiplexer, right, you could start, because you would have a 6 to 64 line decoder, 64 AND gates, and that's all you need to it. 6 bits of select. So that's multiplexers. If you have any questions, please let me know, and if not, I'll see you guys in the next lesson. Thank you.